All right, are the slides visible to you guys?
Yes, sir, visible.
Great. So what we'll essentially be doing is we'll be starting off with a new chapter, which is on mechanical properties. Uh, Most of it, I guess, you would be familiar with the concepts, but it's essential to streamline them in context of what you have learned so far. So starting from the mechanical properties, the most important thing is the elastic deformation. Let us say that I have a rectangular bar with me as shown over here in this stage. This is the initial stage. And I apply a certain amount of force onto this bar. If you see, I have magnified this region over here in terms of the arrangement of atoms. Now, if I apply, let's say, certain amount of force onto this material, here certain amount of force is being applied onto this material, there would be a displacement. The block would get elongated or displaced from its original position. And if you look at the bonds atoms in this region, you would see that the bonds are stretched in the direction of the application of force. Now, as soon as you remove this force or unload this external force that is being applied onto this sample, you would see that the bar gets back to its original position and the atoms also get back to its original position. This behavior is known as the elastic behavior. And once you have to plot the force versus displacement graph and you have to show the elastic behavior, you basically represent it in a reversible manner. That once you start loading, applying force, there is certain displacement. The moment you reduce the force, there would be a zero displacement. The material would get back to its original position. This behavior could be linear, which is known as linear elastic behavior, or this could also be non-linear, but it could still be the elastic behavior as in the case of rubber. This is the elastic deformation. Moving on towards the plastic deformation in metals, again you have the same rectangular bar that is stationary at the initial position, and you have this region of atoms that you have looked into. The atoms are equally spaced apart, they are following a certain order, as you already know. Now, if a small load is applied onto this block, this load is greater than the load that was applied in the last slide, and you would see a greater deformation in the material. But this deformation is essentially, if we looked at it at a micro level in terms of the atomic arrangement, you would see that there is an elastic and plastic deformation. Elastic deformation is essentially due to the stretching up of the bonds. But you would see there is shearing of planes that have taken place. Planes have sheared along each other, so bonds stretch and planes shear as a result of this application of greater amount of force, which both includes elastic and plastic deformation. Now, once you release the load, you already know that the atoms would get back to their original position as in the case of elastic deformation. But the sheared planes, there would be a deformation, permanent deformation that would be there due to the shearing up of the planes. Planes would still remain sheared even if the force has been removed, and this deformation that is due to the shearing up of the planes is essentially the plastic deformation or the permanent deformation. In terms of graph, if you want to have a look, you would see that this is force versus displacement plot. Up till this point, your behavior was elastic, linear elastic. And then when you entered into the plastic region, this is the plastic behavior, which is not a linear behavior. And when you release the force, the the body would not get back to its original position, which is this position. There would be a permanent deformation, which is measured by this length. This permanent deformation or plastic deformation is basically associated with the shearing up of the planes. All right, clear enough?
सर ये जो क्या नाम है लीनियर इलास्टिक होगी
जी
सर सेकंड में, ये क्या दोबारा उसी प्लेस जगह पे आ जाएगी? तो फिर आपने कहा कि ये परमानेंट डिफॉर्मेशन भी हो जाएगी।
नाउ देयर आर टू कंपोनेंट्स ना, एक अगर आप इस फिगर को देखें,
नो सर, आई
bonds
एम टॉकिंग अबाउट ग्राफ।
जी ग्राफ की क्या बात करें?
आपने कहा कि दोबारा उसी पोजीशन पे आ जाएगी, तो फिर परमानेंट डिफॉर्मेशन कैसे हो जाएगी?
दोबारा उसी पोजीशन पे किस तरह आएगी? ये लीनियरली इलास्टिक जो है ये वापस इस जगह पे आएगा, इधर ग्राफ खत्म होगा, ये जो है ये परमानेंट डिफॉर्मेशन होगी आपकी।
ओके सर, सही होगी।
When your force is essentially zero at this point, there is still a deformation in the material. All right?
राइट सर।
Again, plastic means permanent deformation again. Now, how do you quantify engineering stress? Engineering stress or tensile stress is average tensile force per unit cross-sectional area. So if you have this block, this is the cross-sectional area. The force applied onto this block, which is the tensile force, divided by the cross-sectional area A naught, would give you the engineering stress represented by this symbol. This could be pounds per inch square or newtons per meter square. All right. Original cross-sectional area before loading. So Ft is the force that is being applied, and A naught is the original cross-sectional area that was there before the loading was applied. How do you quantify engineering strain? Engineering strain represented by this symbol epsilon. When a load applied on a body, it deforms, as you already know. The deformation or change in length per unit original length is called strain. For example, if you have this body and the force is being applied onto this body such that the body elongates by this white region. This is the elongated region. So this is the original length L naught. The elongation is change in length by 2 on this side and change in length by 2 on this side. So how would you quantify your strain? Your strain would be the total change in length divided by the original length. That would be your strain. And I need not to remind you that strain is essentially a unitless and dimensionless quantity. Now, stress strain testing. How does a material behave when a load is being applied onto it, and how does it resist? Is basically gauged by the stress strain testing, uh, which is also known as tensile test. What you normally do is that you have this, in simple words, you have a specimen and you basically apply tensile load onto the specimen and start measuring the deformation as the load is being applied. So as the load is being applied, you are measuring the deformation until the material fractures. With this data, you basically have a stress strain plot. Uh, a typical tensile test specimen is of the dumbbell shape. You have different standards for this tensile specimen. Uh, this is just to give you an idea of how the tensile test specimen looks like. The time, in order to have the uniformity of results, there are different standards with exact dimensions that need to be followed if you have to follow a particular tensile test. In a typical tensile test machine, you essentially have a load cell that is being used to apply calculated load onto this specimen that is mounted in the tensile testing machine. There is this extensometer which is used to measure the strain as the sample is being stretched. At times, you will not find this strain gauge installed onto this tensile specimen. Rather, you measure the displacement of this machine with regards to the original position. That is, this moving crosshead movement would give you the displacement. So the force measurements are associated with the load cell, and the strain measurements, they are associated with the extensometer. Once we have the data of force, or in other words stress and strain, you can have a stress strain plot for the tensile testing. Now, typically you could have these two kind of tensile stress strain plots. On y-axis you have stress, on x-axis you have strain. There is one kind of behavior where you have the linear elastic deformation, and then there is certain amount of plastic deformation that takes place, after which the material fractures. This is one kind of behavior that you could have. Another kind of behavior that you could have in a stress strain plot, depending upon the material you're using, is that you have a linearly elastic region, that you have a linear region, and then you have the sudden fracture region. These two kind of behaviors you could have. Now, let me ask you a question, that out of these two, which one do you think shows a brittle behavior and which one shows a ductile behavior?
सर जो पहला ग्राफ है वो डक्टाइल और दूसरा ब्रिटल है.
Brittle.
Very good. So if you have any ambiguity regards to what a brittle material is or what a ductile material is, this is a ductile material, and this bulb is essentially a brittle material. What is the difference? Solid materials that can undergo substantial plastic deformation prior to the fracture are called ductile materials. This is significant amount of plastic deformation that you are visually seeing for the material essentially fractured. In case of brittle materials, negligible plastic deformation before the fracture takes place. So if you see, the amount of plastic deformation is almost negligible before the actual fracture takes place. So brittle materials, they won't give you any indication before the fracture would essentially take place. It would be a catastrophic failure. Moving on to the stress strain curve, different regions within the stress strain curve. Let's say I have a ductile material, aluminum and copper, or aluminum or copper, and we have a stress strain plot. This is a typical stress strain plot where I have highlighted different regions. OA, this is the region which is the elastic region in this ductile stress strain curve. A is the elastic limit where Hooke's law is being obeyed. That means in this region, force is directly proportional to the displacement. All right, and K is the constant. Anyways, so in this region, Hooke's law is being essentially obeyed. And the slope of this linear region is known as the modulus of elasticity, or Young's modulus of the material. It basically gives you the, or defines the stiffness of the material for you. Moving on, point B. How do you define point B is a critical thing. It is something we'll be looking at in the later slides also. Just to give you an information, this is 0.2% offset. That means 0.2% of the maximum strain. At the maximum strain, you take the 0.2% of the maximum value of the strain, and over here you mark the value and draw a parallel line that passes through essentially the curve which is known as the uh, the yield strength of the material. B, which is the usable elastic limit for engineering purpose, is known as the yield strength sigma y of the material. This is the stress which induces little deformation in the material. This is 0.2% offset. And OC, as I've already mentioned, is the permanent strain in the material. So from the origin till the point OC, you have the permanent deformation in the material. All right. So from origin to C is the permanent deformation in the material. Now, important thing over here is that as you are increasing the stress, as you are raising the stress, the deformation is increasing. So plastic deformation, strain hardens the material. Plastic deformation essentially hardens the material. So in order to deform more, you have to increase the stress until you reach to this maximum point. So up till this point, you have to increase the stress in order to deform the material. After this point, the necking phenomena starts. The diameter of the material starts to reduce. So that's why you see a decline in the stress for the further deformation until the material fractures at this point. All right. Essentially, the stress is still needed, but as compared to the stress at this point, you require a similar value of stress for a higher deformation because your diameter has essentially reduced or your stress has essentially increased, in other words. This is the ultimate tensile strength point or maximum tensile stress point, and this is the fracture point. Moving on, how do you define the Young's modulus? Young's modulus essentially is stress over strain for the region where you have straight line in the stress strain curve. It remains constant in the linear region of stress strain diagram. And slope of a stress strain plot, E or Young's modulus, depends upon what? If you remember in the first chapter we discussed, or this is the linear elastic region, stress strain plot, and the slope of the stress strain plot would give you the Young's modulus. Now, if you remember the interatomic separation and the force curve in the first, the point where the bonds were formed, slope of the curve at that point would basically define your Young's modulus. So a higher Young modulus as compared to weakly bonded material having a relatively shallow slope for a force separation curve at the point of typical comparison of Young's modulus of different materials. You have metals having high Young modulus. Steel normally has a Young modulus of 220 gigapascal. Gigapascal is 10⁻⁹. Ceramics also have high Young modulus, relatively low Young modulus due to their GG.
सर आपकी आवाज में डिस्टॉर्शन आ रही है सर, अचानक रुक जाती है और अचानक फिर आ जाती है।
सॉरी
सर आपकी आवाज सही नहीं आ रही।
कब से सही नहीं आ रही बेटा?
सही, जो आप यंग मॉडुलस आपने जो ग्राफ से स्टार्ट किया था ना,
तो बेटा you should have told me at that point.
सर हम देख रहे थे कि कहीं सही हो जाती।
आप सबको इश्यू आ रहा है?
No, sir.
Yes, better then you have to check back on your internet connection. If the problem is
yes sir
जी
sir आ रही है
और सर इशू सब
distortion आ रही है
is there anyone who is not having an just a minute, is there anyone who is not having an issue? No one. All right, let me check my internet connection then.
yes sir
All right, can you guys hear me?
Yes sir.
आवाज बेहतर है अब?
Yes sir, now it's better.
All right, great. So I was referring to this Young's modulus part. Young's modulus, as you already know, is the slope of the stress strain curve in the linear region. So the linear elastic region, the slope of stress strain plot is basically the Young's modulus. And what does it depends upon? The slope of stress strain plot, if you recall chapter 1, depends upon how strongly bonded or how weakly bonded your atoms are. This is the point where, or this is the distance on the x-axis where the bond forms. At this point, if your slope of the force separation curve is shallow, you will have lower Young's modulus. But if your slope is higher at the point where the bond is formed, you would essentially have a higher value of Young's modulus. So it is dependent upon the bond strength of a material. The Young's modulus or the stiffness of a material is dependent upon the bond strength of a material. All right? Clear enough?
Yes, sir.
Yes, sir.
Right. Now, comparing the typical Young's modulus of different categories of materials, metals and alloys, they usually have the high Young modulus. Ceramics also have comparable Young moduluses. I mean, depending upon the exact material, the range would vary. Young modulus are normally expressed in gigapascals. Steel, which is the most commonly used material, roughly 220 gigapascal is the Young modulus for steel, the medium carbon steel. Obviously, different kind of steels would have different variation in the value, but not as much. A generic value is this much. Polymers would have relatively very low Young's modulus, primarily due to their ductile nature. And composites, the values would vary depending upon which material you are referring to, or what is the composite made up of. So metals and ceramics have almost similar Young's modulus. Polymers have much smaller Young's modulus. Yield strength, as I'd already defined, is stress at which noticeable plastic deformation has taken place. The American standard is that you use a 0.2% offset. How do you do that? You take the 0.2% of maximum strain value. So this value over here is essentially 0.002 of the maximum strain. What you do is that you draw a line which is parallel to the original curve line. This line. This is a parallel line drawn which is passing through 0.2% offset, 0.2% of maximum strain. The point where this line, parallel line, cuts the curve, the original tensile stress strain curve, is essentially your Young's modulus, or yield strength, the value of the yield strength. This is basically the point where you could have noticeable plastic deformation. That is the limit of stress that is being used as a design value in the engineering purposes. For usable elastic limit or for engineering purposes, you use this yield strength value. Yield strength comparison, again, it would be in this yield strength of different metals would be expressed in terms of megapascal. Polymers would have lower yield strengths as compared to metals. Why is there no yield strength mentioned against ceramics? G. Why is that no yield strength is being mentioned against ceramics?
सर ब्रिटल होते हैं वो.
G. Ceramics are essentially brittle in nature. Now, moving on to the next part, these are the different regions of the tensile stress strain curve. Fracture point corresponding to the strength, corresponding strength is known as fracture strength or fracture stress. So this value would be known as fracture stress or fracture strength. Ultimate tensile strength or ultimate tensile stress is represented by this point, the highest point in the peak. It is also known as UTM, ultimate tensile, UTS, ultimate tensile stress or strength. Beyond this point, necking phenomena, neck starts to form in the sample. Before this point, there is no necking. Plastic deformation is taking place, but there is no necking. Beyond this UTM point or UTS point, you have this necking phenomena that is taking place, and then his neck sharpens, and at the fracture point, this neck is almost at its sharpest at the point of fracture. So necking starts after M, which is the UTS point. If you compare the tensile strength or the ultimate tensile strength of materials, metals would have higher, followed by ceramics, polymers would have the lowest, and composites, depending upon the nature of the composite, would have a range of tensile strengths. Now, finding the Young's modulus, you have an example for you. A piece of copper which is originally 305 millimeters or 12-inch long. So the original length L naught is 305 mm, is pulled in tension with a stress of 276 megapascal. So the stress being applied onto the material is 276 megapascal, which is 40,000 psi. If the deformation is entirely elastic, you are in the elastic region, what will be the resultant elongation, that is change in length? And for this, you have been given that the Young's modulus of the material that you're using, copper, is 110 gigapascal. You already know you have to find change in length. The relationship that you have is Young's modulus is essentially stress over strain. So you have kept stress on this side and multiplied strain with the Young's modulus. And strain, you know, is change in length of the over original length. I have to find out the change in length, so I'll make change in length as the subject of the formula. Once I make it subject of the formula, I'll have stress multiplied by the original length divided by the Young's modulus. All the three values are given to you: 276 megapascal, 305 millimeters, and 110 to 10 to the power 3 megapascal. This would give you an elongation of 0.7 mm. So this is the elongation that has taken place. All right, is this clear to you guys?
Yes, sir.
All right. Mohammad Hassan, could you have your camera off, please? Mohammad Hasnain.